Hi, my name is Daniela Corona Garcia, and today I'm going to explain how I did the second part of the first experiment of the Mariottes bottle. It's important to mention that this is a continuity due to the fact that we are going to apply the knowledge that we acquire and also we're going to use the Mariottes bottle that we built on the first experiment. But what actually we're trying to do, so we're trying to use the Mariotte bottle in order to calculate the gravity that the flow regime does. So we all know that the theoretical value for gravity is 9.81 meters per second square, whereas the gravity that we acquired was 5.74 meters per square, plus minus 0.6%. We notice that this is a huge value, and later on in this video, I'm going to explain really what happened and why, and what can we do better next time. So why are we trying to double check the value for gravity? It's important to mention that the Earth is not a complete sphere, so it is not a sphere that the mass is distributed equally. So there is not the same mass. So in consequence, there's not gravity. So in the poles, there's more, and on other parts, there's different. But the value varies a little bit. It is an important value in order to take into consideration for climate change, for example, but it is not like a really big thing if we think about it. But in contrast to the value that we obtained, that again was 5.74, like for example, it varies like 9.79, things like that. And again, we obtain that value because there are many factors that alter the way that we measure the values, and it is important to mention that we use the method of the least squares in order to do it. So we're going to explain how actually. But first of all, what's gravity? So gravity is like an object or that has a mass pulls another object. It's important to mention that every object has, every object that we see has a mass. And although we don't perceive like the gravity like really tearing us apart, it's important, and that's why the planets go around the sun and things like that. It's important to mention that gravity is everywhere. It was discovered by Isaac Newton, as we can see in the image, and he came up with this formula. It's important to mention that although it was discovered, the idea of gravity like really a long time ago, it is still used today with Albert Einstein, with different theories, like the one that says that relativity theory. Sorry, I was searching for the name. It's here. But we're also going to talk about microfluidic devices. So microfluidic devices are devices that are really small that can change the way that we perceive health industry, medicine, among other things. But how they promote the idea of having like a device insert that can give you a better idea of how the Mariottes bottle works. So it is a new and more recent appliance of the Mariottes bottle. So if you have the idea that a Mariottes bottle gives a certain flow rate constant, we can determine the administration of a certain type of medicine, for example. So what we use in this experiment, the Mariottes bottle, as I say, chronometer, ruler, tape measure, or fructometer, in this case was ruler, and water. For the experimental setup, it was the same as the last one. It's important that you see all the parts of the Mariottes bottle. But what we did with the bottle, was that we changed its age by going up and down the straw. So like in first it was 2 centimeters and 3 and 4, and we calculated for every 0.5 seconds the amount of water that had go down and down. And then we graphed it. So as you can see here, we also took measurements of the device's diameters. So the D small is the one of the straw, the D big is the one of the bottle, the A in is the one that we obtained in the first experiment, the A out also, the A tube, Also, and the AH also, you can see that A out is the area from the drain tube that we determine by the diameter D. The A in is the cross-sectional area of the bottle, and A tube, the cross-sectional area of the central tube. So remember that we use this, and AH we use by resting A in minus A tube. So once we have that, we did the experiment and put all the quantities that we obtained in the graph, in the tables. So we see here H is 3, 4, 4, 5, etc., etc. Then for the experimental analysis is where we are going to apply the method of the square roots, the squares. So in order to do so, we used an Excel. So it is important to mention that the experiment that I mentioned before, and it is made to do it like several times in order to have a more precise result, but in this case, we only did it once. Also, we only use one value. We did the experiment for one table, as you can see, and we use the value that we obtained for every one of the other tables to calculate the plus minus. That you can see in here that when we did the graphs. That's because it is a really long process and we wanted to skip time. So we did everything from here, and you can see that it is 0.06, the error. And you can see it here, the VH error. And this is a percent error that we acquire, and then we use the linear fit. And we did all the graphs in Excel due to the fact that Venus wasn't available for my capacity of my computer. So you can see here everything that I mentioned before. We did a graph for every one of the experiments. No, sorry, these graphs are from H to S. So we only did like that, and we also did a linear fit. We did the graphs for every one of the table, and then we used the VH that I mentioned, the 0.06%. Here it is, and we calculated the measurements, and later we did the linear fit. So in here you can see that it is the value here, 0.6. We use different formulas, and you can see that here they are, and the value that we obtained. We did only a very few dots, and if we use more, it could have been more precise. So later on, we use this formula for the for gravity. It's important to mention that B that we obtained here is a constant for the formula, and we did the calculations, and we obtained 5.74 plus minus 0.6%. Although it's not a really close value, it is because it is not, we use only 5 points as I mentioned before. We could have repeated also the experiments more times. And there are many, like I could have written the experiment wrong. Also, it's important to mention that there was a leak on the bottle, so that could have also increased the flow rate, and I didn't perceive that because although I calculated the diameter small, there was not enough water coming out. No, there was a surplus of water coming out from the diameter. And it is important to mention that we were able to check, to double check the theoretical and the experimental value for gravity, but it does not match in reality. We have a lot of things that influence the value, but it's important, but we often take those variables out and we have to take them into consideration. Also, we could have approximate more the ruler to the bottle in order to have a more precise value.